Hi, I am SB sir, and I'll teach you the pressure volume changes of lung. The pressure volume changes of lung. So it's a very important topic. The pressure volume relationships. So why do we stress on this pressure volume relationships? Because it's always a change in between these two. So we know that lung is a closed space. Lung inside the lung, it's a closed space, and here pressure and volume has to remain constant. We know for ideal gas, when the gas doesn't have ideal gases don't have the property of contraction and shrinkage, or for an ideal gas, this pressure volume is always constant. So if you increase the pressure, the volume has to go down. If you decrease the pressure, the volume has to go up. Why they always act in couples, so act like couples, the pressure and volume? Because why does this happen? Because of some physical laws, because of some physical laws of physics tell you that because the air doesn't have the ability to contract or relax by itself, so that air, if here more pressure is built up, the volume has to go down. So if you suck in air, your cheeks, the muscles of your cheeks goes low. If you decrease the pressure in your air in your mouth cavity, your cheeks go inside. Why does that happen? Because there is low pressure and the volume has to go down. You have sucked in air from your mouth cavity, your cheeks are getting down. So if you can so if there is a if the, so this volume can contract, so the membranes go down. So that happens while, if you put some more air in a bottle. Say I put some air in this bottle. The bottle has atmospheric air. So this was the density of, so say this is the density that I have drawn in green. These are the density of molecules present in the bottle. Now if I put in more additional air, so the molecular densities, so I'm putting in some more additional air here inside the bottle. So I'm putting in some more molecules of air. So now the pressure will increase. But if the bottle is made up of elastic fiber, if the pressure is increased, the bottle will expand. But if it is made up of glass, it cannot expand, but the pressure gets increased. If the volume remains constant, if it is made up of glass, if the volume remains constant, there is a sharp rise of pressure. But if the volume can increase, the pressure release will be the pressure increase of pressure will certainly increase the volume. If the thing is elastic, it will increase the volume. The bottle will expand and it will get round. It will get round. So there is a relationship of this pressure and volume. So if the pressure goes up, the if I put pressure here, if it's an elastic if it is an elastic thing, the volume has to go out. The air has to go out. If this pressure is if this was made up of glass, it would not have happened. But because this volume can shrink, so if I increase this pressure here, the volume goes up. If I lower the pressure here, if I suck in air, the volume goes down. So there is a relationship of pressure volume relationship that goes in any containing air, in any container that has air. So lung also has that. So what is the pressure of the air inside the lung? When the lung muscles are not contracting, it is atmospheric pressure. The pressure when this chamber is not under any expanding force. Say if it is an expanding force, the muscles of respiration are now contracting, so it has an expanding force. So there is a negative pressure building inside this chamber. a negative pressure building in inside this chamber. It is an expanding force. The muscles of inspiration are contracting, so it is trying to increase this volume. The muscles are trying to increase this volume, so it has a negative pressure inside it. And negative pressure will suck in air. That happens during respiration. But if this volume is contracting, if the muscles of inspiration has now stopped contracting and has started relaxing, the volume goes down, it compresses the air goes out. So the air goes out into the atmosphere, it comes from the atmosphere. So any negative pressure that is built inside is actually, any negative pressure is relative to atmospheric pressure. So if I say that the air pressure inside this lung is minus 5 centimeter of water, so I say this minus 5 is below atmospheric pressure. So it's not this absolute, when I say this minus 5 centimeter, it's not absolute pressure that I am saying. I am saying that it's minus 5 relative to atmospheric pressure. We know atmospheric pressure is 760 millimeter of mercury. So minus 5 centimeter of water. So the values are not it is a millimeter of mercury, and this is centimeter of water. So you can, but you can add a little bit. If the minus 5, it may be minus 2 millimeter of mercury. If I say it's in mercury, it will be minus 2, around minus 2, because centimeters and water and millimeters of mercury are not equal. So it may be around 2 millimeter of mercury. So this 2 millimeter of mercury is this is a negative pressure, and I'm denoting this sign by negative. So it is less than atmospheric pressure by minus 2. So the actual pressure inside the lung is 758 millimeter of mercury. So this was a concept about pressure, and this negative pressure is actually a suction pressure. It will pull up. If the mouth of the lung is open, if this mouth is open, it will pull in air. If the mouth is closed, it cannot pull in air, and a hiccup kind of thing will happen. If this is a forceful expansion of volume, the air will try to move. The mouth is closed. we take a hiccup like that. If the mouth is closed, if this mouth is closed by the hood of the epiglottis, and we suddenly contract this lung volume, with a sudden contraction, air will try to flow out in a burst, and it will burst open this mouth, and then we say that we can cough like that. We suddenly decrease the volume, build in a huge amount of pressure, and then open the hood like this. The hood opens like this, and there is a coughing kind of thing. There's a forceful expulsion of the air. The coughing kind of thing happens, and air suddenly in a burst goes out, and we cough. Actually what we do is that we build in a huge pressure inside the lung, and then throw out this air in a single attempt. And so if we can, there can be numerous examples of coughing. If our muscles of respiration gets tired, so we can't pressurize this chamber hugely. So the coughing like this, short coughs will happen. If you can cough more, expand with a huge sound and a forceful air, and this type of cough, how can this happen? Because your muscles are now very good. You can cough very strongly. And this coughing, why I'm telling about these things, because these are actually protective reflexes. When you forcefully expelling this lung air. Why? Because there are some molecules which is irritating your lung air passageways. They are irritating your nasal passageways. So you sneeze to expel that irritating substance. Maybe it's a dust particle, maybe it's some chemical that is irritating, maybe it's some bacteria or some other molecules, other infecting molecules that have come inside your body, and gets deposited in the nasal epithelium or in the laryngeal epithelium or in your trachea. And to get rid of this volume, we cough, we forcefully expire air, so that we can with that air running all along the tube upward, you can expel those irritating substances, those foreign substances that has entered your body through your air. So these are actually protective reflexes that gets going while we have to remove out, just like a brooming. And there are brooms out there. There are brooms out there in this respiratory tract. Brooms means they will continually, these brushes will continually move outward like this. They will move outward like this. If something gets deposited, they will move outward like this, and these brushes will expel those substances in from the mucus, and we see the cough and the sneezes coming out, because they are black things, and those dust particles getting embedded in the mucus, and that comes out, those trapped foreign things getting trapped in the mucus of the membranes, and these are getting brushed out from the trachea. So now I'll be explaining you this diagram. So this diagram has, say, three colors. This is the orange color, this is the blue color, and this is the red color. So this red is inside the lung, and it has an atmosphere. It is equilibrated with atmospheric pressure of 760 millimeter of mercury. So this is the intra-alveolar pressure. The intra-alveolar pressure, the red portion. The intra-alveolar pressure equilibrated with atmosphere. There is no effort of inspiration, no effort of expiration. So atmospheric pressure will be equal to the lung intraalveolar pressure. It will be 760. If there is an effort of inspiration, it will go down. If there is an effort of expiration, it will go up by 762. Up by 762, say, down by 758, down by 2 millimeter of mercury, say 758. So this is the intraalveolar pressure. And this membrane, this blue colored line, is actually the pleural membrane, the internal pleura, as we call. And between this is the pleural fluid. The blue color is a pleural fluid. It's a fluid. And here, one of the, this is very vital, because this is one of the spaces where lymphatics drain. So if you have any disease where the body barriers break and the fluid comes out of your body, and this fluid gets drained into the lymphatic systems, and because this lymphatic systems has openings here also, and because there is a negative pressure, so the body gets this pleural membrane, this pleural space, the intrapleural space accumulates fluid from throughout the body. So if you have edema somewhere, say in your abdomen or in your legs, and pleural fluid is draining into the lymphatics of those from those areas, and the lymphatics are receiving fluids, and it can drain here, because there is a negative pressure inside this intrapleural fluid, and this negative pressure leads to suction of those lymphatic drains, and the fluid will accumulate here. So if there is a so this is it's a negative zone in our body. This negative zone, from anywhere, if there is any, if your body becomes edematous, then also this pleural fluid will get accumulated, because it's a kind of suction inside your body, and this intrapleural negative pressure is because there is always opposing force of the chest wall. The chest wall always tries, because it has elastic properties, the chest wall always tries to get outward. It has elastic properties to expand. To expand the chest wall, if it is in a living system, our chest wall is always is all inside our living system. Say in a healthy human body, the chest wall is always pulled upon by the lung. The lung always pulls up. The lung has its own elastic recoil. So there is a balancing action always going on. The chest wall guy trying to go outward, and the lung tries to get contracted. So both these balancing actions, the balancing actions of the chest wall as well as the lung, this is always the case. And so there is a negative interpleural pressure, the negative interpleural pressure, the pressure, interpleural pressure. I'll read out this this little bit paragraph. The pressure within the pleural sac, the pressure exerted outside the lung, the pressure is exerted outside the lung, this pressure actually expands the lung. The elastic recoil of the lung is there, but it opposes this negative pressure. It will always pull up the wall of the lung outside. The pressure exerted outside the lung within the thoracic cavity, usually less than atmospheric pressure at 756 millimeter of mercury. This pressure is always less, so there is always a negative pressure. So this tube is representing all the airways which are delivering air into the lung. The thoracic wall is drawn, the thoracic wall with all the ribs here, the thoracic wall. This is the pleural sac, and this is the lungs. So just remember this picture, the colors, the saffron color, the blue color is the interpleural space, and the red color, and this is the tubes, the trachea, bronchi, bronchioles, the tubes. Now I'll this is also from Sherwood. Now just a brief illustration. This is from Sherwood. You don't have to draw those lungs, those rib cages. Just this illustration will do. So no movement of air will be there if the atmospheric air and the lung air has the same pressure. So air will neither go out nor go in because it has the same pressure. So this is no movement of air. But during that stage also, there is the intrapleural pressure is always below the, because the intrapleural pressure, the negative intrapleural pressure is actually balancing. It is always a balancing act that is going on inside our living system. The lung has no pressure, it has no buildup of pressure, neither it has no suction of pressure. But the pleural pressure will always be negative. This in if we now expand the chest volume, it will build up greater negative pressure. So it is 756 here, it is 754, it is 754, even lesser, so lesser than 756, because there is an increase in the size of the thorax, and that there is a more negative pressure build up here. Due to this negative pressure build up in the interpleural space, and these membranes are fixed just like two glass slides and having water in them, you cannot separate out those glass slides. Just this thing happens here. The two membranes has in between these two membranes you have fluid here, and the fluid will not allow these two membranes to separate. So if the thoracic cage goes outward, the pleural membranes, both these pleural membranes has to go outward, because between these two pleural membranes you have the fluid, and the fluid will not allow these two pleural membranes to separate. If I put inside water here inside this pleural membrane, if I inject some water inside these pleural membranes, the lung will collapse. So that is called hydrothorax. If there is accumulation of fluid here, the lung will try to collapse because their negative pressure will no longer be there. The lung will collapse. If I put in some air here inside this pleural membrane, the lung will be filled with air, and it will be we will call it pneumothorax. So whatever damages takes place is because there is a permanent force in this blue portion. A permanent force is there. So that permanent force can be negated, and that permanent force, if that pressure is negative pressure is no longer there, the lung will collapse. And you can fill this volume by air, by water, and then the lung will collapse. The lung will collapse by its own elastic recoil. So from here, this is the inspiratory portion. The thoracic cage has expanded, and because the interpleural negative pressure, the lung pressure has got down to 759 from 760, and air is sucked in. And this is during expiration. The thorax has got to its original position with this air volume, because air is sucked in. So the air volume has got increased. The air is more air is present here, and in that position the size of the thorax is getting down. With that air inside the lung, the size of the thorax is getting down, so the air is getting compressed, and the volume because of the shrinkage of volume, there will be a more pressure, 761 pressure, and air will go out. So this is a process, a very simple illustration. This is from Sherwood. You can draw this simple round curves and avoid the necessity of all those longer drawing of those rib cages, diaphragms, and all those things, and just quickly illustrate the thing. Now I'll go into this thing. This is a little bit of conceptual thing, and here two pressures are drawn. It's the intraalveolar pressure and intrapleural pressure, and this is a zero pressure line, zero pressure line, zero pressure line. The dotted line is a zero pressure line, so it is the atmospheric pressure line. The intraalveolar pressure goes down while we inspire. This is the inspiratory phase. The green phase is the inspiratory phase, and this is the expiratory phase. So inspiratory phase, the air goes up. Inspiratory phase, the air goes up, the air gets sucked in. Why the air gets sucked in? Because inside the alveoli, inside the lung, the pressure is negated. There is a negative pressure buildup, and so air goes in. And while the air goes in, while there is a flow, as the air is getting in, the pressure is getting normal. Pressure is getting again to 760. So this is getting to it is at the pressure getting downward because of the contraction of the muscles, the expansion of the volume. It is going below, the flow is there, the flow is there, the flow is there, air is getting inside, air is getting inside, the pressure is getting to normal. So the point 3, as you see here, the point 3 is the no pressure line. So here you stop inspiration. So there is no movement of muscles. Here you stop. This is a volume. This is a static volume, and these are the expanding volumes. These are the while the pressure got down, the volume is getting expanded, and this becomes a fixed volume. It is after inspiration. After inspiration, now expiration begins. Why expiration begins? The pressure inside the alveoli is getting more than the atmospheric pressure, and so during this phase expiration begins. The volume gets lowered, expiration begins. While the air goes out, the pressure again goes to normal. So this is the intraalveolar pressure demonstration of why this intraalveolar pressure changes like this, and this is the intrapleural pressure, the pressure here, the pressure inside the pleura. So this is not like the shape of this wave. It is like this because the intrapleural pressure has to be throughout this inspiratory phase from 756, which is always lower than this atmospheric pressure by 4 millimeter of mercury, and from this 756 it will go down to 754, the intrapleural pressure, because intrapleural pressure is dependent on the expansion of the thoracic cage. The thoracic cage has to continually drive the pleura out. So the pleura, there is always an expanding force on this pleura, the expanding force on this pleural space, and this pleural space, the pressure inside will go up, will go down to here, and then rise during the phase of respiration while the chest are coming back to normal. So this is the expanding force of the lung that is always throughout this inspiratory cycle. So there is no flow of fluid here. There is no fluid. So if there is flow of air here to, so that the pressure again gets normal, there is inside the intraalveolar spaces there is flow of air, but inside this pleura there is no flow of fluid here. So the pressure has to go down. The pressure will go down and it will go up. It will go up in the expiratory cycle. It will go up to the expiratory cycle so that the lung can compress. The lung can go down. The lung can compress the air. The lung can compress the air. This compression is reflected by a pressure rise. So this is the intrapleural pressure. Intrapleural pressure. from 756 it is through in inspiration it is getting down to 754, and from 754 it is again getting to 756. But this difference of the intra-alveolar pressure and the intrapleural pressure is called the transmural pressure gradient across the lung wall. Across the lung wall, the transmural, the wall is the mural. So across this mural there is a pressure difference which operates. Across this mural, across this wall, there is a pressure difference across this wall. This is the pressure difference across this wall, across the lung wall. So this pressure difference actually widens here, and the pressure difference actually shrinks here, and it widens here. See, this arrow is widened. So this transmural pressure, the transmural pressure, what is this? Is the concept of transmural pressure. Why? Because inside the alveoli and inside the interpleura, it's outside the alveolar spaces. This is intra-alveolar pressure, this is outside the alveolar pressure, outside the lung. Outside pleura is outside the lung. Pleura is the intrapleural space where the fluid is there. This fluid is there. So across the lung, across this lung, there is a pressure difference, and this pressure difference is called this gradient of pressure difference. This gradient increases, this gradient shrinks. Okay, this gradient shrinks here. See, this gradient shrinks here, and as this gradient comes to its original, this is end of expiration, this gradient is this much, while during expiration this gradient, while at the end of inspiration, this gradient at the end of inspiration, just before the start of this gradient has got increased. So the transmural pressure gradient has got increased. And because there is more lowering of the intrapleural pressure, and the lowering continues in the pleura, while the alveolar air, because of the air supply, is approaching zero. So the gradient is increasing. So this is all about. So I'll just read out this few points of this curve from the book, whatever the book inside the book is written. During inspiration, intra-alveolar pressure is less than atmospheric pressure. This is a very fine point. Everybody should know it by now, that during inspiration, intra-alveolar pressure is less than atmospheric pressure. So the air happens to come in, otherwise air will not get inside. During expiration, intra-alveolar pressure is greater than atmospheric pressure. Why expiration happens? Because intra-alveolar pressure, the pressure inside the lung, is greater than the atmospheric pressure. At the end of both inspiration and expiration, as well as expiration, the intra-alveolar pressure is equal to atmospheric pressure, is approaching the zero pressure line. It is equal to atmospheric pressure, because the alveoli are in direct communication with the atmosphere. Because the glottis is now open. The mouth of the lung is now open, and it is in direct communication with because air is flowing out. Because with this pressure changes, air is flowing in, and it is flowing out, and they're in direct communication, and so they become equal to the atmospheric pressure. And the air continues to flow down its pressure gradient until the two pressures equilibrate. The air continues to flow along the pressure gradient. If the pressure goes higher, the air continues to flow out. If the pressure goes low, the air continues to suck in. So this is in direct communication with the atmospheric pressure. Throughout the respiratory cycle, intrapleural pressure is less than intra-alveolar pressure, and this is called the transmural pressure. Throughout the respiratory cycle, intrapleural pressure will always be lower than the intra-alveolar pressure, and this is called the transmural pressure. This gap actually widens here, actually shrinks here, the transmural pressure. But throughout the respiratory cycle, these two pressures will always, this alveolar pressure will always be greater than the pleural pressure. Pleura is intrapleural space, is actually a negative pressure zone inside our body. Thus, a transmural pressure gradient always exists. I'm reading out the fifth point. The transmural pressure gradient is always existing, and the lung is always stretched to some degree. Because of this transmural pressure, lung will always stretched. there is always a suction, there is always a suction pressure. Whatever air you are putting in, whatever air you are putting in to increase the pressure, but there will always be an expanding pressure or expanding, because lung also try to recoil this expanding this these expanding forces outside, these expanding forces outside will always be there, and there will always be difference in the transmural pressure throughout this respiratory cycle. So I stop here with this all these concepts of pressure. Thank you.